The next one I want to look at actually has to do with a model of Steph Curry's basketball shot. Because my claim is you see linear combinations. If you understand modeling and you can look in the world around you, you see linear combinations all over the place. We're just not used to interpreting them that way. It's kind of hard for you to see this particular diagram. I've actually created this in my notes. It's a diagram of a free throw. Free throw, I don't know if anybody has watched basketball before. There's this really beautiful thing on a basketball court called a key. And then there's like usually something like this. And then you've got the hoop right there. And then there's some stats to kind of realize. So if you were looking at it this way, I actually made this thing took me like, don't ask me how long I spent on this freaking diagram. It's like ridiculous amount of time on this thing. I also read the whole NBA. Like I spent a ridiculous amount of time figuring this out. I actually looked at Steph Curry's height. I did a statistical analysis of length of arms. I did that based on his, I spent a lot of time doing this because I wanted the thing to be actually accurate, right? So it ends up happening that the particular thing that I was modeling, Steph Curry stands 14 feet away, and I don't know if anybody knows this off the top of your head. Do you know what the length is from the line to the, I think it's 14 feet. I think that's a free throw. And then this particular thing I said was 10 feet in the air because the NBA regulations that I found, and I actually found that rule book for the NBA, say that the hoop is 10 feet in the air. And then Steph Curry was, I think, 6'3", and I actually, I took some balls out and I did this, and then I watched Steph Curry shoot on YouTube, and I kind of figured out how extended his arm is when the ball's leaving his hand. I did it in slow motion, and I found out and then I did an analysis of how long his arm is based on the fact that he's 6'3", and then there's statistical tables that tell you how long people's arms are, right? And so I analyzed this to be something like 7.25, 7 feet and so here you've got this basketball player here's his head, there's his arm, and he's standing at, I don't know how I guess he's doing a fade back, I don't know how that works. So this is going to be 7.25 feet. And then, from there I spent a little bit of time, I actually read a study of a guy that was doing Newtonian what is called fluid dynamic analysis of the way that the air travels around the ball. I spent a few hours looking at that paper to figure out how detailed I should go. I ended up ignoring all of that because I don't need that level of sophistication for this particular model. But what ends up happening is I can have 3 data points. So I can have the data point, if we're thinking about this is my axis, is this the time axis? Yeah, so is time a part of this conversation? No. So then if I talk about the second derivative and we think about second derivative acceleration, is that with respect to time? No. It's with respect to movement along the x-axis. In other words, if you had a set of lights, so here's the phenomenon. Steph Curry's at the free throw line. He's about to shoot the basket. He takes the basketball, throws it up. If you had a set of lights directly above the basketball that projected a shadow down onto the ground, the x value would be the distance away from Steph Curry's feet when he stands on that free throw line. So at 14 feet away, the shadow would be right above a ball, which would be in the hoop at that point, right? Okay. Could you guess what the h-axis would be? Height. So it would be the height of the ball. And my claim is I did 3 things. I actually looked at, and I don't remember how I got this one. It's in my notes somewhere at home because I spent some ridiculous amount of time thinking about it. So now I get 3 particular points on this thing. I said this is going to be 8, 13 point. Oh, you know what I did too? Yeah, I know exactly how I got these. What I did was I looked at 3 different values, and then I created these. So I'm going to make a claim. Let's model the height of a ball using the following polynomial. And this is where things get really confusing, and I want you to get mad at me, okay? Because now we're going to be using a's for scalars and x's for vectors. Yeah, this is what it's really funny. It's not funny at all, actually. Okay, so the whole idea, what do we call this particular function in our standard approach to this material from way back when in our lives? Yeah, it's a quadratic function in standard form. And my claim is each of these things we're going to think about as a vector, and each of these things, the coefficients, we're going to think about as a scalar. And not only that, given that some ridiculous mathematician spent literally hours of my life putting these together, these are now the coefficients that I found. I mean, I give myself a solid C- for this. The real thing that I would have to do is I'd have to sit down, film Steph Curry shooting 1,000 shots. I'd just have him shoot 1,000 shots over like a period of days. And then I'd collect all that information. I would film it on a video camera. Then I would break down every shot on the video camera, and I would come up with an entire data set. And then from that data set, I would take statistical averages about the height that he shoots from, the speed of the ball in the upward position as the thing goes this way, and then the way that it goes down, right? And then from that standpoint, I could then come up with a statistical model where I could change parameters depending on how tired he is, what quarter of the game is, and that would give me an accurate way to talk about how Steph Curry does. Or I could be a freaking math teacher and I could be like, here's a parabola. We've never seen this thing used in life, but we're just going to assume that we'll use integer coefficients because that's interesting. Right? There are people that get paid by the NBA to do this type of analysis. Right? Yeah. Yeah, so here's what I want to do. What are my inputs in this particular vector that I'm analyzing there? Yeah, so let's call this one x1, we'll call this one x2, and we'll call this one x3. So now what I want to do is I want to actually create a vector, which we're going to call h of x1, h of x2, h of x3. It's a discretized vector of a continuous space. Formally speaking, is this thing supposed to be discrete or continuous? Continuous. But the moment that I choose a select few of those, what happens? Chop it up. I chopped it up into pieces, right? How would I calculate each of those? What is the corresponding value of each of those things? Well, the first one was 7.25 times what? 1. Times 1. What's the next one? Times 1. What's the next one? Okay, there's a pattern arising, right? Okay, what's the next one there? Yeah, so why don't I do this? Why don't we just make this really, really painful? One of the best ways to remember stuff is to feel a lot of pain while doing it, right? Yeah, it's called the Protestant work ethic, right? Okay, so what's the next one? What's the what's the first x value that I'm going to sample at? 0. What's the second x value that I'm going to sample at? 8. What's the third x value I'm going to sample at? 14. And then what's the last one? Why is it not negative 9.8? Is this with reference to time? No. If it's not with reference to time, does negative 9.8 have anything to do with it? Yes, underneath, if you were to go back into the parameterized space of t, right? Yeah, but formally speaking, this is a change in velocity in the height of the ball as the ball moves across the field to get from the free throw line into the hoop, right? Okay, so what do we do in this one? We take the x0 and what do we do to it? Square it. And then the next one would be negative 0.975, right? What am I doing? With each of these things, what am I doing? I'm literally just sampling the function at this, right? In your previous lives, in order to get this information, you had to do each one of these samples individually, right? Yes. But now what we're saying, you remember what I said about vectors, how I want you to think about them? Sets of scalars that are organized in a really, really fancy way, right? Well, now we're doing 3 function evaluations simultaneously. Do you see scalar vector multiplication and vector addition? Can you skip right to it? 7.25 times what vector? 1. Vector of 1s plus 1.5610 perhaps times 814 plus negative 0.075 times Yeah, 0, 8, 196. And then just for giggles, tee-hee, a tee-hee.
Wait, I think we're in the 14, but you didn't put a 8.
Oh yeah, sorry. Yeah. What would the corresponding, well, let's do them all out together. If we're thinking about this in the standard form, this is where we have to depart from this particular notation, right? So be careful with this. This notation is ass backwards because the a's are the scalars and the x's are the vectors. But in linear combinations, we're going to think about the x's as defining the scalars and the a's as defining the vectors. So let's go ahead and do this. What's the first x? Yeah. What's the first a? Yeah. And how big is that a? It's a 3 by 1. What's the next x? Yep. And then what's the next a? Yep. And then what's the last one? A3. Here's a claim that I'm going to make. Every linear combination is actually just a particular solution to a matrix vector multiplication problem. What is the matrix? Well, how did I pull the matrix out? The first vector in my list becomes the first column. So the first vector would be 1, 1, 1. What's the next one? 0, 8, 14. And what's the last one? Yep, and for those of you that took my Engineering 11 class, this is what we call a Vandermonde matrix. It was part of your lesson 2, lab 2, I think, when you did the thing of test matrices and you used the flip LR. This is a very, very famous matrix. It also, people spend a lot of time on this matrix because it shows up all over the place because it happens to be that matrix shows up when evaluating polynomials, and polynomials are quite good at approximating continuous functions in a way that behaves well on a computer because polynomials are constructed from addition and multiplication. Computers do that well. Yeah.
But then that was called augmented.
Say it again.
But that was called augmented.
I hate augmented matrices. If I saw an augmented matrix on the street, I might like run away from it or go up to its face and like shake it. You're going to see this later in life. Yeah. Augmented matrices are a convenience for teaching people that don't know what matrices are how to solve linear systems. So I will not, you can use them and we'll get to that, right? But I despise augmented matrices. We'll talk more about that later, right? Yeah, I cannot stand those things. Yeah. So let me ask you this. So what did we say about each of the vectors in a linear combination? The first vector becomes the first column. The second vector becomes the second column. The third vector becomes the third column, and so on. What about the individual entries of the column X? Where do those come from? Okay, and what would those be in this case? Okay. 1.561. Okay, so let me ask you this. What did we just do? We created a linear combination where the inputs were my discretized input, my domain, and my desired output vector was the corresponding heights of the ball as Steph Curry hits from evaluating each of the particular instances at the given input that I did, right? And so in this case, that's where I actually got those things when I calculated what is the corresponding B that solves this linear combination, aka this matrix vector multiplication problem. Well, in this case, it's 7.250. That one's not bad, right? Because all that's annihilated. This one's kind of interesting, 13.498. I don't know if that's the maximum. And then this one's 9.998. What the modeler who chose to model this problem, what did they assume? What's true about the ball? It's literally going right up through the bottom edge of the ball is through the top part of the hoop, right? Because the top part of the hoop's at 10 feet. So it's literally 0.002 inches below the top of the hoop. Not a bad model, solid C-, I agree. Yeah, go ahead, Misha.
Spend all those hours trying to make this, you're really just spending all those hours trying to like find that vector of
trying to find the coefficients that makes this an actual accurate model.
Yeah, that's like a general linear systems problem, right?
General linear systems problem would be if I sampled more. I mean, it depends on how you do it. I could either not do this third one, in which case I'd get a rectangular matrix, or I could put more x's in which case they're called tall and thin, or short and fat. This is set in the short fat matrix, right? I might call it short and wide, and then tall and slim. Tall and narrow.
Your entire time just looking for that.
Yeah, I mean, this is true about modeling. This is one of the things. This is why I get so mad at mathematicians, because what a mathematician will do is they'll just give you these numbers because what they care about is the structure of the function. But the problem is most students don't have the intuition or the desire to go spend 20 hours of their life to actually create useful functions in their life, right? Yeah, and so that's what I was doing. I was trying to get that to be done.